how passing an electric current through an electrolyte can cause non-spontaneous redox chemical reactions to occur. This process can be reversed in this section. We will discuss how spontaneous redox reactions can produce an electric current. You are undoubtedly familiar with the various types of batteries used to power flashlights, watches, and portable electronic devices. These compact portable sources of electricity are voltaic cells, devices that convert the chemical potential energy of spontaneous redox chemical reactions into electric energy.
In this video, we're going to show you how to set up a voltaic cell. The cell itself consists of an anode and a cathode and a salt bridge. So you're going to want to go ahead and put your anode and your cathode metal strips into the appropriate solutions. Next, insert the salt bridge. Go to the voltmeter, plug in the leads, and turn it on. You'll notice that there are a lot of choices on the dial. You want to choose the 20 DC volts setting. With the cell set up and the voltmeter turned on, it's now time to measure the voltage of the cell. Connect the red lead to the cathode and the black lead to the anode. Record the voltage in your notebook. If your voltmeter doesn't have clamps like the one shown in the video, you might have to use your fingers to hold the test leads onto the metal strip so that you can get an accurate, consistent reading. Notice how important the salt bridge is to completing the circuit for the cell. Removing the salt bridge immediately makes the voltage drop to 0. It is possible to connect 2 of these cells in a series. To do this, use a wire to connect the anode of one to the cathode of the other. Doing this will result in double the voltage of the single cell, and in this case you would have enough power to light up an LED light. When you're finished, make sure to disconnect your cell, turn off your voltmeter, clean everything up before you leave.
When 2 different metals are involved in a redox reaction, the metal higher in the activity series will be oxidized and give up electron, reducing the casting of the active metal. A salt bridge, a tube filled with a non-reactive electrolyte, takes the place of the porous divider in equalizing the charge.
Each year in the United States alone, billions of dollars are spent to repair and prevent the damage to metal mines caused by erosion, the electrochemical deterioration of metals. The most familiar example of corrosion is the rusting of iron and steel, but corrosion also manifests itself in the silver tarnish and in the green molding that forms on copper, brass, and bronze. The reactions involved in the corrosion of iron are quite complex, but are believed to occur in the following steps. Iron in contact with moisture in the air is oxidized.
MSJ Chem. In this video, I'll be looking at the standard electrode potential. We'll start with a definition. The standard electrode potential is the electrode potential in volts measured under standard conditions relative to the standard hydrogen electrode. Standard conditions are solutions with a concentration of 1 mole per decimeter, gases at a pressure of 100 kilopascals, and a temperature of 298 Kelvin. Let's look at an example. On the left, we have a zinc half cell, which is composed of a zinc electrode in a 1 mole per decimeter solution of zinc 2 plus ions. The zinc half cell is connected by a wire and a salt bridge to the standard hydrogen electrode on the right. We also have a voltmeter in the circuit which measures the electrode potential of the zinc half cell. Because zinc is higher in the activity series than hydrogen, the electrons flow from the zinc half cell to the standard hydrogen electrode. Here we have the equations for the reactions that occur at the electrodes in each half cell. In the zinc half cell, we have the oxidation of zinc to form zinc 2 plus ions. In the standard hydrogen electrode, we have the reduction of hydrogen ions to form hydrogen gas. And here we have the overall equation for the reaction. As you can see, we have a reading on the voltmeter of negative 0.76 volts. This is the standard electrode potential of the zinc half cell. Let's look at one more example. On the left, we have a copper half cell, which is composed of a copper electrode in a 1 mole per decimeter solution of copper 2 plus ions. The copper half cell is connected by a wire and a salt bridge to the standard hydrogen electrode on the right. We also have a voltmeter in the circuit which measures the electrode potential of the copper half cell. Because copper is lower than hydrogen in the activity series, the electrons flow from the standard hydrogen electrode to the copper half cell. And here we have the equations for the reactions that occur at the electrode in each half cell. In the copper half cell, we have the reduction of copper ions to form copper metal. In the standard hydrogen electrode, we have the oxidation of hydrogen gas to form hydrogen ions. And here we have the overall equation for the reaction. If we look at the reading on the voltmeter, we have a voltage of positive 0.34 volts. This is the standard electrode potential of the copper half cell. So let's have a summary. When a half cell with a metal above hydrogen in the activity series is connected to the standard hydrogen electrode, the electrons flow from the half cell to the standard hydrogen electrode, and the electrode potential is negative. The example we looked at is the zinc half cell connected to the standard hydrogen electrode, and that gave us a voltage of negative 0.76 volts, which is the standard electrode potential of the zinc half cell. The standard electrode potential values can be found in the data booklet. All these metals are above hydrogen in the activity series, therefore they have a negative value for the standard electrode potential.
Chemists often express the tendency of a substance to form a stronger or weaker charge when placed in an electrolyte as a substance. Standard electrode potential, that was called. Anyways, the half cell containing the hydrogen apparatus is a standard hydrogen electrode.
you want to ask is what is the cathode and what is the anode?
Right.
So in our case,
That's right.
Okay. I
well,
just put it in the.
the lithium is
PlayStation
actually
for my
2% of the cell mass. So it's like the salt in the salad. It's a very small amount of the cell mass and a fairly small amount of the cost. But it sounds like it's big because it's full lithium ion, but it really, like our battery should be called nickel graphite because it's mostly nickel and graphite.
This video is all about how you set up the equipment for electrolysis and what all the parts need to be made of. This is how we normally set up electrolysis. So what you've got is you've got a beaker with a liquid inside it, and in that liquid you put two rods which are connected by a power supply. The two rods we call electrodes. The negatively charged one, that is the one that's connected to the negative side of the battery, is called the cathode. So the negatively charged electrode is called the cathode, and the positively charged electrode, the one on the other side, is called the anode. The liquid we refer to as the electrolyte. So they're the four things that you need to be able to label on an electrolytic cell. In terms of the electrodes, what they need to be made out of is something that conducts electricity in its solid state. So for this, we normally use metals because metals as solids conduct electricity, or you can use graphite because graphite, although it's a non-metal, does conduct electricity also. The electrolyte has to be made out of an ionic substance, and that leads back to our definition of electrolysis previously. But the electrolyte has to be in a liquid state. So I have two options. Either I take my ionic substance and I melt it into a liquid, or I dissolve it in solution, in water. So what you need is you need those ions being free to move in that solution. And if that ionic substance is a solid, then they've got no chance of those ions moving. That's it for the basics of how to set it up. Check out the next.
Go. The anode of an electrolytic cell is positive, whereas the anode of a voltaic cell is negative. However, the following conditions are true for both electrolytic and voltaic cells. Oxidation occurs at the anode, reduction occurs at the cathode. The anode emits electrons to the exterior, the external circuit. The cathode receives the electrons from the external circuit.